Welcome, 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 my Matilda, Kat, Cassidy, Wences, Maxine, Nolan, Dante. Welcome, welcome, welcome. Welcome, Maria. Welcome, welcome. We are just getting stuff plugged in. Let's share a screen. It's our old favorite screen, our class. Let's turn on the chat. Love the chat. Let's make my screen a good size. Let's get the participants window working. Then, after my little video area is hidden from me, turn on a video of me for the world. Welcome, Finn. Welcome, Liv. Welcome, welcome. Folks are arriving here more than on time. Early, like I was earlier than I've ever been. I can never remember being. Kat, what's your question? That's in section 4.1. Let's talk about it all together, because then it'll help other people out. All right, we've already got a great homework question from in the room. More folks are showing up in the Zoom. Good things are happening as we chime 11. Welcome, Chantel. Welcome, Abby. Welcome, Aim. Welcome, Kira. Welcome, welcome, welcome. Oh, you'll see me make some faces today. I have kind of a weird, like my head hurts in a weird way. Since I got sick in mid-February, I have a bad ear and it's like worse. And then last night and today it feels like, you know how sometimes when you have an ear problem or a sinus problem, they're like related. And sometimes that like feels like it's in your jaw. Now I've got a weird ouchy jaw. So you see me making funny faces today and grouchy faces. It's because my head is feeling weird. And there's a little bit of pain inside of it. I'll try to maintain a poker face if anyone's talking to me, so it doesn't look like I go, ah, in response to your ideas. But so watch out for funny faces today. And welcome, welcome, Nicole. Welcome, Peter. Welcome, 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 Ryder. Welcome, 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 welcome. People are here. This is so great. While people are settling in, think about if you have an interesting question to ask about recent homework you've worked on or anything else you've been working on. Let me know. We've definitely got one question to look at already. Let me go gaze upon it. It's in the first section of chapter 4, so we'll look there. Oh, wait. Before we look there, and before I get your question, let me just double check the plan for the day. I did also double check it earlier, but let's look together at our schedule. It's always a good place to peek to see what our dreams are. We've been a little off schedule lately, but only a little. And let me show you where we land today. Last class, the 26th of February, our last February class, we did talk about that second section of chapter 4, the complicated idea that we can use statistics to describe we can analyze how a statistic, like a sample mean, would vary from sample to sample. When we do that, we get what's called a sampling distribution. So that was the big discussion last class. It took the bulk of the discussion time, and we began our discussion of the binomial distribution, and our plan today, well, it's not a surprise. Hold on, let me get into the correct email zone here. Let me get logged into my proper editing things account, me, the PCC version of me. Go back here, reopen the schedule. Now there's PCC me and I can edit things. Yeah, so there's more discussion to be had about this binomial distribution. So we're gonna just kind of copy that stuff and paste it there. We're going to continue and wrap up our binomial distribution discussion today and talk about the sampling distribution of a sample proportion That's not a very long discussion, so I think even though it's two things, we should have time and energy for both. And Maria, did you have a question? Possible. 425B. Okay, possibly. Well, we had another question that was, I think, was it 4-5? Is that right? 4-5, Kat? 4-5? Okay, so let's take them in that order, 4-5, and then if you're still feeling that question, Maria, we'll look at it. I'm heading over to our links. Oops, first I'm going to turn, oh no, I'm good. It looks good. I'm going to go to our text. I'm heading to chapter 4. First section, normal distribution. Fifth problem in this section. Hey, welcome, welcome. I hear the doorbell ringing from the world of the Zoom. I'll crank up my speaker here, so if you want to use your mic, go ahead and get my attention, or of course, any other way, chats or hands or whatever. And those of us in the room will make sure to find you and answer your question. Okay, GRE scores part 2. Want to look at this one briefly? Yeah. Okay, this is great. Any of these homework questions from any of the sections in chapter 4 are great class discussion questions because we're learning about a lot of stuff in this chapter. Every section, we learn about a different probability distribution that's useful in a kind of a different setting. And they're all kind of related to each other, just enough to make the differences harder to see than they need to be. So it's always good to kind of look back into the homework to light up our discussion a little more. I'm going to go ahead and take a screenshot of this GRE scores part 2, and we're going to open it up in the class notes and work through just both parts, just to get a quick sense of how these work. Always good to get a peek at how stuff works with some support. I'm going to content. Our class notes are right there in the course material. Look at that, our class notes are getting pretty lengthy. We've got a lot of stuff we've worked on. Let me go down to that, the last part. And now we're here at Monday, March 3rd. Uh, 4.1 homework question. That's going to be a setting so we can see it, a heading. The old table of content, GRE scores part 2. Okay, cool. So here's the question. In a previous exercise, they showed us 2 distributions for the graduate something examination. It's like the SAT, but that you take as you leave undergraduate with say a bachelor's degree, and you want to go on to get a master's or a PhD. GRE is the test for graduate programs to look at for your math and reading skills, but like at a college level. There's the face I'm going to make when my face hurts. Ow. Oh, man. Maybe I should have taken some painkillers. Ow. So the distribution for GRE scores for the verbal part of the exam is the first thing. N for normal, mean 151, standard deviation sigma 7. That's the verbal part of the exam. And they've got for the quantitative part of the exam, a mean score of 153, slightly higher, with a standard deviation that's also slightly higher of 7 and 67/100. Use this information to compute each of the following, and they give us 2 short little descriptions. The score of a student who scored in the 80th percentile on the quantitative reasoning section. Let me just set this up Ralph style. Whenever I see one of these problems like this, let me get my pen out. Oh, goodness. Yeah, I think my head is messed up. Do I go to the ear specialist, the dentist, just the regular doctor? Ugh. But when I see this part of the problem right here, N, oh wait, no, A, sorry, A is about the quantitative reasoning. That's this one here. That's this description. So it's a normal distribution with mean and standard deviation noted. Right there in my notes, I'm going to draw myself a lovely little bell. You know, it doesn't have to be the most beautiful bell in the history of bells, but bell-like. In the center, I'm going to note that's 153 points on that part of that examination. And standard deviation wise, that's 7 and 6700. So somewhere in my notes, just have those values. Takes me a little more time to write those on the computer than it would with a pen on a piece of paper, because my mouse writing just is not as good as my handwriting. Now, what they want here is the 80th percentile, and that's the idea that we've got to be familiar with as far as how to see it in my picture. Remember, a percentile is a value that cuts off whatever percentage of, in this case, area under the curve below that value. So if I just grab my little highlighter here and I start to color in, that's all the way up to the top, and then I just keep going up this way. That's half the area. That's about half the area. And then I want to color in like, you know, 3/10 of the area up here. So a little more than half of the area up in this direction. Looks like it should be something like that. And the idea being that this number right here, the 80th percentile, would be like the cutoff that would cut off the lower, you know, right there. Oops. Wrong pen. Right here, we'd have, dang it, what's going on with my computer? Computer, work with me. This would be, that's the shaded in 80% of that area. See that? And then that is, there it is. That's my little, I want to know this value right here. That's the plan. Okay. And then, like, the nice thing about my note-taking style here is that once I've got the picture, I've got an idea what I need, I kind of have everything I need for the calculation using technology written right there in orange. So now I'm going to head over to GeoGebra. And let me just, yeah, I'll just head over there. Hold on. Clean up a little bit of the mess on this screen. I'm going to go via our path in our class. I can go to the links section. Good old GeoGebra Classic link is right there for me every time. Head to the probability calculator where the normal probability calculations live. And hey, I picked a good place to make my notes because now I can see right there my mean is 153. I set that as mu. My standard deviation is 7 and 6700ths. I set that as sigma. 7 6700ths. I need the area below a value because of my left shading. So I go to that left-sided, the little bracket pointing down at the lower values there. Oh, I gotta select it. And then since I'm looking for the cutoff is going to be the number that goes here, because that'd be the number that'll cut off, you know, wherever it is on that scale. So I just type in my 80% or 80/100ths in the field where the percentages live, this one. I type 80%, and the moment I've got that typed, our little buddy GeoGebra calculates that the cutoff score, if you want to round it off to the nearest whole point, which is I think how they score these tests, would be 159. Yeah, pretty relaxing. So let me just get this as a quick shot of this for my notes. It's got both my little drawing and my calculation that I use to get this done. Cool. clear that stuff, go back here. Come on, friend. Oh, wait, not Rafi. Hard A. Using sorting out the values and using GeoGebra. And bam, there's my thing. So I would say, what's that number? Let me see it a little bit bigger here. 159, the 80th percentile of GRE quantitative. Oh, thanks for the fixed spelling. Scores is about 159 points. Just like that. Yeah, relaxing. Once things are working for us with really the setup, I think like the most crucial part here is just knowing when they're talking about percentiles that what we need is that area off to the left of that cutoff score. And once that's part of our working knowledge base, we've got a lovely technological tool to help us out with the calculation. Does that help? Question asker? Oh, okay. Want to look at part B as well? Or do you want to just trust yourself with what we've got? It's a similar question, just the drawing's different. Maybe I'll make the drawing, but maybe I'll leave the calculation to you all. Part B here, let me just clear off my mess. Now they're focusing in, get my little pen back. I'll change colors to, I don't know. Pink is next to orange here. A student who scored worse than 70% of test takers in verbal reasoning. Okay, the verbal reasoning scores have a different distribution, so the mean and standard deviation are different. So I've just got to be careful. My drawing is going to look a little different. Different center is going to be 151 for the mean. Well, my drawing is not that good. But it's my notes. It doesn't have to be the best drawing. 7 for standard deviation. The numbers here are a little easier to write in just because no decimals. That's just a 7. Cool. And they want the score of a student who scored worse than 70% of the test takers. So it's going to be a cutoff number with 70% of the scores above it, right? So you're below 70% of these test takers. I'll color in that 70% worse than. That's just going to be, well, these people who got very, very high scores. There's 50% cutoffs right there. I'll get about 20% more of the remaining area. Something like that. Maybe even a little lower than that. I don't know. It's not the best drawing in the history of drawings. But I'm working with a mouse here. Don't worry, this really ugly, brainy goop of noodly mess I'm making, I've learned that it makes it easier to read once you're done with that goop. It just flattens it out. And there's our cutoff score right there. That's the number we want to find from GeoGebra. That cutoff that gets us 70% of our area above. Yeah, and so that's the main thing on these problems is just making sure I've got a good sense of what I'm looking for, and then I can get it calculated using technology. So in honor of note keeping, I'm going to take that, setting up B. Okay. And then I would just, if I wanted that number quick and accurate, I just go over to GeoGebra, same thing I did before. I just got to change the mean, change the standard deviation, change the direction, and get the value. Yeah. Anybody want to see that process to double check anything, or are we good to go? Good to go, or check the process?
Check.
Check. Okay, cool. Let's go. I've got this little picture to help me out. I'm heading to GeoGebra. I already forgot what the mean value is, so I gotta look back at my notes. 151. Thanks, Maria. I remember the standard deviation is 7. That's the one that was easy to type, or sorry, write. The cutoff is the upper. This one, I just wrote the number upper 70%. So like that. And the score is about 147 3/10, but I think they only have whole number scores on these tests. So I'd round that off to 147. Yeah, Maria?
Also do that it's less than the 30%, 15, that works. Or should you not do it that way?
That would work perfectly well. If I switch this around to 30% right here, looky there, it's 147.3, etc. Yeah, so if you're looking above for 70% or below for 30%, that's the same. Yeah. And in olden times, when people used a table of values, you always had to look for a value below. So it was important to always make that switch. Nowadays, it's really just preference. So let me go back to my notes that matched my picture before. 70% there. Grab this. I'll just grab that much of this picture. 147 about. And GeoGebra says that cutoff question mark is about 147 points. The 30th percentile of scores, right? 30th percentile below 70% of test takers scores. And there's my picture to back it up. Yeah. Relaxing. The relaxing part comes when we're careful, just being very careful to set up the picture so you know what you're looking for, and then making sure when you get your calculation done with GeoGebra, hey, GeoGebra gives you a less artistic yet more accurate version of your picture, and you should be confident that if all the numbers match that you wrote down in your picture, that you got a great result from GeoGebra. Maybe I'll just call the dentist at some point today. Should I come into the dentist? Oh, great. And then there's a question about the 7th question in 4.2. Want to peek at that together? Sound good? Let's look at that too. I love homework questions. They're the best. Let's peek on into the next section of the text. I might need your help navigating question 7 in 4.2. Let's go down to 4.2, sampling distribution of a sample mean. Let me just double check that we're looking at the same question. You mean this weights of pennies question? Weights of pennies? Weights of pennies? Yeah, okay, great. Always just double checking that I'm not wandering off to the wrong, you know, if someone's on the PDF and I'm in the computer version, sometimes we're looking at different problems. Okay, I like this weights of pennies question a lot because it uses both the techniques and ideas from the first section of this chapter and the second section. So let's make that explicit how they're different. It's an excellent review question for our last 2 topics that we discussed in full. Let's check it out. Homework question 4.2. Get that into the weights of pennies. Cool. Okay. The distribution of the weights of United States pennies is approximately normal, with a mean of 2.5 grams and a standard deviation of 0.03 of a gram. Just in my notes below, I can say penny population, right, is going to have, because that's just all the pennies in the US. sorry, let's make it more specific. USA pennies. The mean, that would be Greek letter mu, if you like the letter. And the value is 2.5 grams. And then we got standard deviation. When I type it, I just go SD, Greek letter sigma. If I want to track that symbol down, I can do that, or use the Greek letters in your notes if they're familiar to you and you like drawing them. They're beautiful. It's 0.03 of a gram. Okay, there's our population information. And now we have questions. Oh, and that's approximately normal. So I could even say N, mu is 2.5, comma, sigma is 0.03. Capital N for this is a normal distribution. Okay, cool. Let's look at part A. What is the probability a randomly chosen penny weighs less than 2 4/10 grams? Just like those GRE score questions, they're just talking about one random penny. We know their mean weight and the standard deviation of all the pennies' weights. We can quickly check this using our skills. So let me get the probability X, that's one penny's weight is less than 2 4/10 grams. X being, see that X over here, one penny's weight is varying normally with mean 2.5 and standard deviation 0.03. Okay, now I'm back in the world of my favorite tool, just getting myself set up to get the calculation done with a nice little drawing. I'm going to try to draw better than that. I'm going to go for an actual flat axis. I'm going to just draw my bell. I went back to orange because copper, kind of orange, coin-wise. Copper color. Pennies are made of zinc mostly, but their color is copper color. A tiny amount of copper in that zinc to give you that pretty copper color. And if I want to do better notes than I did last time, rather than bad handwriting, I'll do some typing here. 2.5 grams for the weight of these pennies. Mean and 0.03 for the standard deviation of these pennies' weights. And I want to know the chance of being less than 2 4/10. So that's a tenth below the mean, which is pretty far down there. That's like more than 3 standard deviations, right? A little bit more than 3 standard deviations. That's like all the way down here. So there's 2.4. And I want to know the likelihood of having a penny weighing less than that. That's my little guide drawing, and I think it should work out pretty well when we use this. Hold on a sec, though. Let me get my notes together here. Just to improve some things about my notes. Let's head over to GeoGebra and calculate this. Again, just always when using technology in your notes, if you're not making the drawing, at least have enough notes that you know to switch the mean to 2.5. And to switch that standard deviation to the penny weight standard deviation. I can tell you the most common mistake I make is just forgetting to adjust one or both of those numbers, and then I just get a completely ridiculous answer. But that looks better. Make sure I'm looking off to the left with the left-sided selection of that little bracket. Then I dump in 2.4, and we are in the world of pennies that are noticeably lighter than expected. That is not a big chance. Down there near 0.04%, if I think in terms of percentages, or down there near that's just 4/10,000ths, if I'm thinking in terms of just the raw probability. Unlikely. So, and that's my notes. Now, and role model wise, if I didn't want to cut and paste, sorry, if I didn't want to take a little screenshot of my work and dump it into my doc, like let's say I'm working on a piece of paper, if I wanted to show my work on paper, I would just write by hand this little phrase, except I'd add one more thing. I'd say from GeoGebra, probability calculator. So if I'm using technology and I don't have the ability to get a quick screenshot, just indicating somewhere in my notes exactly what technology I used. And as long as all the numbers that I plugged into my technology are right there nearby, a nerd looking at your work or yourself looking at your work in a few weeks should be able to recognize how you got the calculation done. That's what notes are for. And, homework is like notes. It's something we do to communicate with our future self about our learning, or even to communicate with ourselves on the day we're doing our learning. Okay, part B. Now it gets a little more complicated. Remember, the second section of our text was about sampling distribution of a sample mean. That describes how means vary from group to group for various samples. So things get a little more complicated as soon as we shift to that perspective, I think on part B. Yeah. Describe the sampling distribution of the mean weight. Symbol-wise, that would be X with a bar on top, or X bar in stats ease, of 10 randomly chosen pennies. And to describe that distribution, we have to know its shape. And once we know its shape, we have to know how to use it mathematically. Spoilers, the shape is a bell curve, a normal curve, and we're going to need to describe its mean value and standard deviation. Okay, let's take some notes here. The samples means, whoa, that's some bad mistyping. I hit caps lock instead of A. X bar is shorthand for varying samples means for samples of size 10. I should probably put that right here. N equals 10. X bar is going to be, well, since the population of pennies has a lovely normal distribution of penny weights, samples of 10 pennies will also have a lovely normal distribution of penny weights. So it's going to be normal. We just need to know its mean and mean of the sample means. And we need to know its standard deviation, sigma, of the sample means. What are those two numbers? And that's what the theory we talked about last class tells us. Mean of sample means, just in general, is always going to be the population mean. It's cool. Samples means are going to be near the population's mean if they're good random samples. And so the mean of all the random samples means is the population mean, which is what number here? Wait, sorry. Oh, sorry. I'm running around the screen too fast. I just wanted to add population right there. Now that we're talking about two different settings, the population is one thing where you grab 1 penny. Now we're also in a new setting, varying samples means for samples of size 10. That's the X bar world instead of just capital X, 1 penny at a time. But see there's our population mean right there. Back in our notes, it's 2.5. So it's a number that we already have. Cool. Now, the standard deviation, sigma, of the samples means, varying from sample to sample, shorthand X with a bar, that's got a little formula. And the little formula is population standard deviation. Divide that number by the square root of the sample size. If you're able to put stars and hearts in your notes, that's where you put a star. It's as soon as you're talking about varying samples means, so you shift over to this world of mean values for groups, different samples, you have to adjust the standard deviation because means are more consistent than individuals. We talked about that a lot last class with a few examples to see how samples means are more consistent than individual members of the population, and in a predictable way that statisticians happen to love. And that's the little formula we get from our notes. Population standard deviation, that's also known as sigma. So that's just a raw sigma, divide square root of n. 300ths is the population standard deviation, square root of sample size 10 right there in my notes. And that's a number that I'm going to use for standard deviation of varying samples of size 10s means. Ooh. Every time I say that long sentence out loud, I'm reminded, yes, this is a complicated idea. And the more I focus on the concept, even though there's all this complicated math, well, maybe it's focusing on both, get the math right and reminding myself what the concept is. For most people, one helps the other stick. You know what I mean? Like if the concept makes sense, then people remember, oh yeah, so there's those extra calculations to do. Or if the calculations make perfect sense, they can say, yeah, and I'm doing all these calculations for this idea. So, or anywhere in the middle, wherever your conceptual or technical thinking goes, just go your path until this stuff starts to feel like it makes some sense. I'm just going to calculate this number quickly with a search engine. But I have to copy it to do that. Copy, internet, paste, go. There's the rounded off standard deviation here. I'm just grabbing lots of decimal places to get at least more than one or two past those zeros, that I don't have to retype the last value by rounding it up. So I'm grabbing about 5 digits just to get out to that little 3 right there. Like a nerd, I just want a nice, wait, Control Shift Paste, is that, yeah. And I could round that, maybe I would round that off to 0095. If I just want 4 decimals, I'd round it up once I'm back in my work. So 0095, standard deviation of varying samples means for samples of size 10, or X bar for short. So really, for the notes though, now I've got X bar. That's the distribution of those varying means. It's going to be normal. The mean of the varying means, mu subscript X bar, is 2.5. And the standard deviation sigma of those varying sample means X bar is 0095 after a decimal. That's part B. And that is obviously tricky until we recognize, oh, when they're talking about sampling distribution of the mean weight of 10 randomly chosen pennies, that puts us into this world. It should be normal. And we can look up what the mean should be and what the standard deviation should be, always knowing standard deviation is going to involve some calculation because it's going to be more consistent than the variation out there in the population. Cool. Then part C is relaxing. Now it's just a question. What is the probability the mean weight of 10 pennies is less than 2 4/10 grams? See, instead of just one randomly chosen penny in part A, we're talking about the mean weight of 10 pennies. Well, now that's not so bad. We know the mean and standard deviations for the varying mean weights of 10 random pennies. So in my notes, I'm just going to write, probability that the mean weight X bar of 10 pennies is less than 2 4/10. So I'm in the world of my sampling distribution. My picture, it's going to look a heck of a lot like the other picture. Let's change the color. blue. Hey, that's not a pen, that's a highlighter. But it'll have a bell shape like before. It'll also be centered at 2.5, like the whole population of pennyweights. Blue pen, please. Thank you, computer. And it'll have the smaller standard deviation 0095 after that decimal. Oops, with a typo. You could change the number, be careful for typos and all this work. It's another easy way to make a mistake. Typos, if you're working like me with a keyboard, or rightos, if you're handwriting this stuff and you miss a 0 in one of these small numbers, for example, that's a really common way that people get one of these problems incorrect, especially on exams and stuff where people are working on the clock. Now here, to get down to 2 4/10, I'd have to go like 10 standard deviations plus, like really far, because that's like less than a tenth of a tenth. The standard deviation is less than a tenth of a tenth. It's less than a hundredth. So 2.4 is like, you got to go like further this way to get down to 2.4. It's somewhere down there, but it's way down there. So my notes are telling me, I bet when I calculate this probability, the result's going to probably just round off to 0. I'm way down there, like more than 10 standard deviations below that expected value of 2.5. Still, I'm going to do the calculation to be a healthy little calculator over in GeoGebra. Oops, I put my little drawing in a place that makes it hard to see it, so my notes are not easy for me. If that's on a piece of paper, mellow, I just stick with it. But if it's in a computer, I just drag it around. Okay, got to adjust my standard deviation down to that 0095 after a decimal. That's my pain face again on my face. It's pain. Doesn't have anything to do with how I feel about decimals or standard deviations. Ouch, gee. And then you can see now 2.4 isn't even on our screen. It's like further off the screen. There's no area visible in our picture at all. And yeah, the likelihood rounds away to 0. It's like less than whatever, half 100,000th to round down to 0.0000 after a decimal. So there we go. Very, very, very unlikely to find 10 pennies whose mean weight is 2 4/10 of a gram or less. Very, very unlikely. Grab my computer buddy here. Get a nice, for my notes, is about 0 from GeoGebra. And there's our result. Relaxing. I mean, relaxing only once all of the sort of analytical and technological steps here make sense. The crucial analytical step for question C happened back in question B, when we figured out how those sample means should vary from sample to sample. When you have that sampling distribution's mean and standard deviation and shape, you have analytical power to answer questions about the probability of a statistic like a sample mean landing in some range you're curious about, like in part C, a very, very low mean weight for 10 pennies would be incredibly rare. That really is 0.0000. Who knows where the numbers end up being out there? You always get a number as a result here, but this one's so tiny that it rounds away to just 0. Well, that's how it looks in my notes. Oh, come on. Please, please. Ouch. Okay. How we doing? Part D is kind of a hard question. Okay, we're doing good, great. So the calculation stuff, I think A, B, and C here, those are the kinds of questions that I would like to put on an exam. They're nice because A and B are in the same universe of pennies. Part A depends on understanding how the normal distribution works for 1 penny, and part C depends on us understanding how to shift over using the central limit theorem to figuring out likelihoods for mean weight of a chosen number of pennies. So those are like ideal exam questions. Part D is kind of a hard question for folks for whom this is new, because unless you're like, even if you've been drawing little bells in your notes like me to help guide your calculations, like me, you're probably always drawing the bell first, then labeling the mean and standard deviation. You're not like busting out a graphing calculator and getting a perfect normal curve formula drawn graph. That's just not what most of us do. So when they ask us to sketch these distributions on the same scale, it's just a little tricky. Let me just show you how I would approach that. I used orange for the population of pennies, like the color of copper, and I used blue for the varying sample mean weights. Right?
Really, like really fast. Can you take me through how to calculate C again?
C?
Yeah.
Yes, and no need to apologize. Whenever a calculation goes by faster than, or like, the calculation itself took a second, right? So what I did was I started with just my notes. I'm in this world. I need the likelihood that that sample mean is less than 2 4/10. And I've got the information from B that the mean sample mean, mu x bar, is 2.5, and the standard deviation of samples means is 0.0095 after a decimal. Then, well, it doesn't take long to re-explain. I made my little drawing that shows, hey, 0.0095 and 2.5, that'll put 2 4/10 way, way below the edge of the picture that I draw. Dumped all the numbers into GeoGebra's normal distribution. So just 0.0095 was the one thing I had to change because I'd already been messing with pennies. Looked for the left and I got 0, rounded off at 4 decimal places. So does that blazing fast version help? Or is there a specific step you need to see?
So it's like the mean of 10 pennies, right?
Exactly.
So does it matter if it's like the mean of 10 versus the mean of like 20?
Yes, totally. If it was the mean of 20 pennies, back at step B, I would have used the square root of 20 instead of 10. So I would have got an even smaller standard deviation. Yeah, exactly. The sample size is a crucial piece of information because it's that division of the population standard deviation by the square root of the sample size that tells us in terms of variation how much more consistent the sample means for that size sample should be compared to all the individuals in the population. Yeah, great question, because that little technical detail, like this is the place where I would put stars and hearts, because to get this work done properly, it's getting that standard deviation properly adjusted that puts you in the correct place analytically. Yeah, great question. And then for part D, to draw these two curves on the same graph, let me just grab a black axis. I'll grab an orange curve. Here's the population. Oh, that's I need my bell to look more bell-like, more beautifully bell-like. That's pretty good. So that's let's call that our population, centered at 2.5, standard deviation 300. It's the same little drawing I've got up in my notes before. So 2.5 here. In orange, please. Or maybe in black. I don't know. Well, let's make that just orange for now. And then the standard deviation of that curve is 0.03. And then to draw the second curve, it's not easy to like just see how to do this without a little work on my part. I can see in my I'm glad I have my notes from before. When 2.5 is centered for the population, 2 4/10 is like, at the very edge of that scale. So let me just write that scale number in there. Right there is about 2 4/10. Okay. Just so we can see how it looks, 2 4/10. Okay. And now to draw in the other curve, that's this one, the varying sample means, it's got the same center, 2.5. So it's going to be a bell centered there. Its standard deviation is noticeably lower, 0.0095. And in the drawing, they're also supposed to have the same area under them. So it's got to be noticeably more slender and noticeably taller. To give me one more clue how to draw it, though, I'm going to look at my GeoGebra work for this part C again. See how it shows the edge of the bell is at like 2 47 for this blue curve. It's more like 247. That's like, there's 2 4.5. There's 2 4.7-ish. See that? I'm trying to draw these in. I don't know. 2 6.5. I'm trying to get a sense of where the edges of that curve should be. As a nerd, that's the best I can do. So it's going to be noticeably thinner and noticeably taller to have the same area. That's my vague attempt. It looks pretty lumpy, but I still feel pretty good about it. The blue one's skinnier and taller. And if you've done the best you can to capture that in your notes, you've done well. They're both centered at 2.5, so I don't have to relabel the center. But this standard deviation is 0.0095, and I can't really label that right there on that tiny little line, but I can give a little indicator that this is 0.0095. Make it blue to match the curve, because I like to have multiple pens in daily life or multiple colors in my Zoom's universe. But see, that little drawing, to a statistician with a doctoral degree, they can kind of visualize that the second they're thinking about two normal curves that have different standard deviations. To those of us who are in introductory stats class and have only been working with the normal curve and its likelihoods for, say, a week of our lives or a week and a half, I think that's the hardest problem here, because it's just a little bit extra kind of graphical thinking about the concept. Worth thinking about, though also actually a challenging problem. I'm definitely going to take a picture of that for my notes. It's not the greatest drawing on earth, but better than nothing. Part B, just paste in the drawing. And it looks okay. You'll see the drawing in the textbooks, results. They drew it with a computer, but you don't have the tools at your disposal to draw that with a computer, because we've never showed you the function that draws that line, like on an algebra graph in Desmos or even in GeoGebra. So it's not easy to draw these without that formula. So it's kind of a hard question. I don't think the stats person would have thought it was hard, but I sure do. Also, because almost every quarter, one or two smart people have asked me how this works. And so I know it's not an easy question. All right, team. E. This one's more like a critical question. Could we estimate the probabilities from A and C? So those are the calculations we did. First, for the penny weights as individuals, knowing that they're normal, we use the normal distribution. Second, for the penny weights, the mean penny weight of 10 pennies varying, and we know it's normal and we can adjust things using the central limit theorem. Could we do those kinds of calculations if the weights of the individual pennies had a skewed distribution? Great. Well, here's a question. Let's take them one at a time. Could we use this symmetric curve to do the probability work if the pennies had a skewed distribution? Would that make sense? If we knew it was like very skewed to the right, like there's like a minimum penny weight, but like occasionally you get like a double weight penny, like they're like rare outlier heavy pennies. Would it make sense if it's skewed noticeably to use this lovely symmetric curve? No, yeah, we would need a different analytical model that took the skewness into account. Ideally, just lots of penny weight data we could use to build that model. So for A, definitely not. Now for C, it's trickier. When you switch over to calculations about probabilities for mean weights in this case, or just mean values generally, you can always use the normal model as long as either the population is fairly unimodal and symmetric, or your sample size is at least 30. So for part C, it would depend if the population's only somewhat skewed, like not horribly skewed, it would probably work, this model. If the population were very skewed, we'd need at least 30 pennies to take the means and have the means vary this way. That's a lot of technical stuff, so maybe part E is also a hard part of this problem. So I'd say we couldn't use wait. If penny weights are skewed, we couldn't use the symmetric normal curve to do a calculation like in A. And then how can I put it as briefly as possible? Though, if either the skewness wasn't too intense, or if we were curious about n equals 30 pennies mean weights, we could still miss with the central limit theorem method from C. Mess with, I meant use. But that's tricky too. Like it's having a sense of what the requirements are for the central limit theorem to work. If the population's normal, distribution of means will always also be normal. If the population's distribution is not normal, so either multimodal or skewed either direction or both, then, well, you need bigger samples for the theorem to play out. At least 30 guarantees the theorem works for any population distribution. And then you can get away with fewer than 30 depending on how skewed or how multimodal something. Tricky stuff. Hey, really good homework questions. We took a whole hour of good homework questions. Maria?
Could you possibly go for 4.25 really quickly, because I got something else a little bit different, so I just want to make sure that I
425B, which section is that one in?
4.2.
Okay.
And then see if we have time.
And what's the name of the problem? Which one is it?
It's right after that. That's not.
What if we talk about it right after the break? Because then we can all stretch, and then I can think about how I can do this as quickly as possible. Yeah, but let's double check things. Yeah, this one also has some little wrinkles in it. So yeah, let's take a break. Let's get back here after 10 full minutes of relaxing. That's 10 minutes past the hour. All right, good homework question askers. Are you ready for a little more? Me too. Let's party. All right, our question on the table is this one. Songs on an iPad, especially B and C, right? Okay, yeah, let's look at this. Look at that, look at that. Thanks again, Elizabeth, thank you. The great teacher of snipping. Get props in my other class too. I say thanks, Elizabeth, and the other class on Tuesday and Thursday. But here we go. This is a homework question 4.2. Oh, let me get that into headings mode so that it'll end up on the table of context. Songs on an iPod. So this is an ancient question from the ancient days when people had something called an iPod. So do you remember when you were like a baby, if you're age 18 or 19 or 20, iPods? Do you remember? Like your parent might have had one when you were a small toddler. They look like cell phones, but all they do is play music. And their screen is really weird and old. Some of them were pre-touch screen even. They had a cool wheel, an old-fashioned fun time wheel. Hey, and Matilda had a great iPod. And your iPod even had a sweet little likable gender. Your little friend, she was great. Oh, nice. Like some people call their car she, you know. That's sweet. You got a good iPod relationship. Okay, but in any case, this is the days before streaming audio and video. So if you wanted to have a lot of songs to listen to in life, you had to store them on your own device. An iPod was an MP3 player that would store possibly thousands of songs, depending on how much memory your iPod had. So suppose an ancient iPod in the year 2012 had 3,000 songs. That's a pretty good song library for an individual person to collect. And you had to collect them yourself. You had to like do the work of loading things on there. The best strategy was to take CDs out of the library, burn them onto your iPod, and return them a lot. One of my friends did that and had like a whole hard drive of like every good rock song. The histogram here shows the distribution of the lengths of these songs. We also know that for this iPod, the mean song length, let me just get this, population of songs, mean length, and standard deviation. The mean 3 and 4,500, so that's slightly less than 3.5 minutes. And the standard deviation for all of these songs is 1 and 6300ths of a minute. That's like 1 minute and 40 seconds almost. So population mean, length, and population standard deviation. Population of songs, song lengths. And you can see in the graph, that makes sense. About 3.5 minutes should be the balance point. It's right in there in the center of that. It's not a perfectly symmetric graph, but it's, you know, it's at the cutoff. You can't have a song that's shorter than 0 seconds. And there's not a ton of prog rock and jazz songs on this particular iPod. You can see once you get past about 5-6 minutes, there's fewer and fewer songs of lengthy nature. And the Yes song that I heard the other day is not on this iPod because it's like 18 minutes long, so it's not even on there. So some songs, most songs that last a whole side of an album. First part A, we didn't get asked about, but let's just talk about a strategy. Estimate the probability that a randomly selected song lasts more than 5 minutes. You can see on the graph, that's just every song length up here in this zone. You can just eyeball that if you like. You could say, I don't know, 10 or 15%, you know, you just eyeball it. Or if you want to get into a more accurate estimation, you could estimate, if you choose for accuracy, you could say, well, there's about 350 songs from 5 to 6 minutes, about 100 songs between 6 and 7 minutes. And then, you know, maybe there's 50 or so more songs altogether for these long, long songs. You could add up all those numbers for estimates and divide that by 3,000, and you get a pretty good analytically informed estimate of the likelihood that any random song is longer than 5 minutes. Now, some of those songs, like Don't Fear the Reaper, are awesome. And you're so psyched it's longer than 5 minutes because it's like awesome the whole time. Others, they start off boring and they stay boring for more than 5 minutes. How'd that stay on the iPod? You could delete them too in the olden days. Okay, now parts B and C, these are where the problem gets challenging as far as the analysis. We can't just use the graph. So let's look at these again, kind of as quickly as possible here was the goal. Part B, you're about to go for an hour run. Friends, give me a little, make you into a list. Ah, wait, what? Oh, I want a little list. Oh, I see I need an A and then I get a B like that. Part A, use the graph to estimate. Smiley face. Hey, smiley face, give me my little smile. There you go. Yeah, smile. Good. Part B, if you're going to go for an hour run, okay, this is unrealistic for numerous reasons, but a math teacher, stats teacher made it. Sometimes they're just pulling things out of their hats in hopes of coming up with a problem. We know our stats book writers like running from all the goo problems earlier in the quarter and the women's running group. So we know she runs. That's good. Good for her. But this is weird. You're about to go for an hour run and you make a random playlist of 15 songs. Well, let me just write that down. N equals 15 songs. What is the probability your playlist lasts an hour, at least an hour, to last for the entire length of the run? That's a weird idea. You could just hit shuffle on the iPod, much like in modern days with any streaming service. You can say, just give me a random stream of cool music. You don't have to say 15 random songs. That's weird. No one does that. So, but a nerd might think that they need a sample size for their example in their stats book they're writing. And you wrote us a free stats book, so you're cool with me. And the hint is there. If you want the playlist to last 60 minutes, so that's a 60-minute playlist. Average mean song length needs to be 15 songs to fill up 60 minutes. I just got to divide, right? 60 divide 15. That's 4 minutes. That's kind of long. That's longer than the mean song length on the iPod. But if we look back at the graph, there are quite a few songs in there that are, over 4 minutes. So maybe if you did mostly pick longer songs and just a couple of short ones, you could get that mean song length of 4 minutes. And then sample and style-wise, that's mean song length X with a bar, yeah, would be at least 4 minutes greater than 4. And right there, twice in my notes, both in English and back here where they said, what should be the minimum average length, right? Average. I wrote mean because that's my style. I could have wrote average. But then in my notes, I'm now in the world of X bar, sample mean being in a range longer than 4 minutes. That means I'm in the universe of central limit theorem, and I got to go use that little standard deviation formula to figure out how the means should vary from sample to sample. Sample size is only 15. That's not 30 or more. But to my eyeballs, that's a very unimodal distribution for the population, and it's pretty symmetric. There's some skewness, but not that much, So it's fine. I'm going to say it's cool. Central limit theorem says sample means vary like, well, X with a bar should vary normally. That lovely bell curve is going to come back into play. The mean mu of the sample means is going to be the population mean. That's cool. And the sigma, the standard deviation of the sample's means, X bar, symbols are a lot. Well, that's the population standard deviation divided by the square root of sample size n. And all that together, that's like how I'm going to use my probability for calculations. Let me just get those numbers. So mu subscript X bar, mean of sample means, it's going to be 3 45/100ths, a little less than 3.5 minutes. And sigma underscore X bar, standard deviation of samples means, should be 1.63, the population standard deviation, divided by the square root of 15. That's just a number that I can get from the internet. About 42/100ths of a minute, 0.42 after a decimal. That's enough accuracy for me. Notice that's lower, a lower standard deviation. It's more consistent than the variation of song lengths among all the songs. And then I can just, if I want to be lazy and not do my little drawing, I can take this information, mean, standard deviation of varying samples means, and I can go figure out that likelihood of that mean being bigger than 4 in my buddy GeoGebra. I'm going to skip the drawing just for time, even though my whole soul calls on me to draw a little bell and draw it out. Just for time, the asker said you can work fast. So 3 45/100ths, a little less than 3.5 minutes, mean song length. 42/100ths, standard deviation of varying, it's the mean of the mean song length for 15 songs from the iPod. That's the standard deviation of the mean length of 15 songs from that iPod. We're looking at being long enough to fill up the whole run. So you got to be at least 4. So 4 there. And that is not very likely, but not impossible. It's about a 9.5% chance, according to my work here, which is actually, I'd roll the dice. I'd just go jogging. And if Burnin' for You by Blue Oyster Cult ends before I get home at the end of the jog, I'm fine. I'll just listen to the rest of it at the house. Or sorry, I'll just put it on repeat or whatever, because that song rocks. Bam, and there's the calculation. Yeah, does that get B? And then if your result, so our result is P X bar greater than 4 is about 0.952, or about a 9.5% chance. Playlist lasts a whole hour. And that might be a little different than the book's result, again, because the book uses like tables in the back of the book. So if it's off in the rounding zone, if they have like 9 3/10% or up to 9 7/10%, anywhere in that range, don't worry. And if they talk about z-scores and stuff like that on their calculation path, it's because they're using the old-fashioned method. Don't worry about those things. Don't be distracted by the ancient methods. Stick with modern methods, unless the ancient methods make sense to you in your reading and you enjoy doing them, and it gives you a feeling of joy to get the same exact result as the back of the book. Then go for it. C works the same way, but they're changing the time on us. So for part C, same exact idea, but instead of 60 minutes and 15 songs, it's 6 hours or 360 minutes and 100 songs. So I'll just put a note for part C. Part C, this is the same as B, though the mean length needs to be long enough for a 6-hour trip with 100 songs. That's 360 minutes, divide 100. X bar at least. And that's what, 3.6? And that's going to be tricky. 3.6 is closer to the, it's closer to the average song length of just slightly less than 3.5 minutes, though the playlist is a lot longer. So is the consistency going to make the further consistency going to make this even less likely or slightly more likely? I don't know. But I would just go in there and adjust standard deviation to X bar subscript, standard deviation sigma subscript X bar. That's going to be, wait, 1.63. Is that the one we had before? Yeah, divide square root of 100. And hey, I can do that one. That's just dividing by 10. So that's going to be 163 after a decimal for the standard deviation. Same mean as B. And then you go do the calculation and you find out the left way. Is that cool? Enough there? Yeah? Mella? All right. These are complicated. So you can see we had like 3 homework questions. That took like half the class. So again, as you're working through problems in chapter 4, wherever you are in that work, I would strongly recommend whatever questions you have, write down off to the side, ask about this one. If it's something we have discussed in class and you're looking like back at our discussion to work through it, also try to like work through it on your own, referring to our discussion only as needed, to deepen your understanding. And if anything we're talking about, whether it's the original discussion or today's discussion isn't clicking or making sense as you're working on these or other problems, just ask. And especially if you've got your work, we can one-on-one is a great way to like look at what you've done and see like, oh, I see at this little stage, this is the crucial point where the central limit theorem kicks in, or oops, you've used the central limit theorem where we didn't need to, and that's thrown you into a little off base. Lots of things can go awry when things get complicated in analysis. So just keep asking your questions and we'll do the best we can to discuss them all. And now we're going back to the world of the binomial distribution that we where we left off last class. We left off right at the end in the class notes talking about we developed this binomial distribution. This was last class's project. The goal being to describe capital K, the number of free throws beloved former Portland Trailblazer Damian Lillard would make out of 3 attempts back when his free throw attempt percentage to date in olden times was 88%. We drew this big, complicated rainbow colored tree. Once we knew that there's only 4 ways this event can go. He misses all 3 free throws. That's making 0. So 0 is the outcome. He makes 1, makes 2, or makes 3 for outcomes 1, 2, and 3. We spent a long time working our way through how those probability calculations work. And then we took a little trip back to Ralph's life as a math major at Portland State University. And we even went through and saw like, wow, there's this really interesting pattern to how the calculations work. It involves kind of how many paths through the tree for each of the outcomes. So how many ways it can happen. You multiply that by however many factors of a success has occurred. So 0, 1, 2, 3 are the factors for the probability of success. And then you multiply that by the number of factors for how many failures happened. So it just goes 3, 2, 1, 0 in the opposite order. That is a complicated, long time to figure out all those numbers, especially in this world, working with this tree by hand. You all helped, but it took the whole team working together to get this done. Now, I did say the last class, you'll never ever have to draw this huge complicated tree in any other setting. You can always use technology for this. So let's check this. Oh, let me I'm gonna continue the notes for this one on Monday right here. Continuing make your free throws. So the date makes sense. And it's in our notes where it kind of makes sense. So we could have asked that same question. Give me the probability for Lillard making missing all three, making one, making two, or making three, as long as he's set with a chance of success of 88%. We could have just using GeoGebra to check our work. Wait, will someone do me a favor? Will anyone in this classroom or in the Zoom room, will somebody pick any one of these 4 probabilities on our list and just calculate it with the nearest calculator? Just any one of them. If you calculate one in the chat, that's perfect, because then we'll have it in the chat to all look at. If you're in the room, calculate any one of the 4 and just hold on to the number for a second. Let me show you, GeoGebra's got binomial distribution in the probability calculator. So if I head right back to where I was just working using the normal distribution, that's the world of the probability calculator, geogebra.org/classic #probability. And where it says normal, that's a menu, and I can pop that open. And there's lots of other options here, like the student distribution, chi-squared distribution, and the F distribution. If you take STATS2, you'll meet those 3 in STATS2. We never see a bunch of the ones on the list below those in either STATS1 or 2. They're more specific and useful in certain settings. But once you get down to this little light gray line, the next one's the binomial distribution. That's the one you're going to be able to use to get calculations done very quickly and very accurately. So I'll select that. And then all you need to do to get your probability distribution figured out, notice when you open it up, there's just n is 20, so the number of attempts for the random event, and p is 50% or half. Those are just set because they need numbers in there. And you can see right over here on the right side of the screen, there's the likelihoods for all the outcomes. To switch to the world of Lillard's free throws, all we got to do is change the number to 3. So just 3 free throws, and bump up that probability of a yes, he made the free throw, to 88% without doing a typo as you do it. And then looky there. How's that for a picture? We can see, let me light them all up. I'm just going to light them all up in bright blue. And that way it makes my lovely little probability distribution up here. The chance of him missing all 3 free throws is less than 1%. The chance of him making only one of the 3 is just a little bit less than 4%. The chance of him making 2 free throws is pictured on the graph. It's about 28%. And the chance of him making all 3 free throws is about 68%. If you checked one of those numbers, did you get the same, you got the same value, right? Yeah, like these are the exact calculations that we drew that huge tree for. So we can really, really quickly get these probabilities calculated without any, tree drawing and complicated sketching and stuff like that. Let me just grab this for my notes. Yeah, just bam. Just to see what's what there. It's so cool. Yay, so good old probability calculator. You're our little friend, or our nice little friend. Okay, and then the next couple ideas in the slides for this section, let me go back to our slideshow that we started last class. It immediately becomes apparent that even if you liked doing the calculations and using the tree, or the formulas that are related to that pattern we saw last class and just saw again briefly, well, I'll show you something. Here we go. Slides. Chapter 4, binomial distribution. Hello, little friend. Oh. So we left off here in the make your free throws slide. We made the distribution. Now we can see it in our class notes, either the by hand version here at the end of our notes from last class, or now lit up in blue with just the numbers, the whole distribution of the probabilities for each outcome from GeoGebra. And then there's an old quarters version of the discussion. So just as a slide for some quarters, I want to rush through that without drawing it by hand. We have that option. But this slide says our binomial distribution generally describes the likelihood of the number of so-called successes, K, out of a specified number, N, of independent success, failure, or any yes-no trials. With P, lowercase p, the probability of a so-called success, well, the remaining probability, if you subtract p away from 100% or 1, you get the probability of so-called failure. N is the number of independent trials, and K, the number of successes. Here's the formula for the probability of K successes out of N trials. That parentheses with N on top of K, that's the section we skipped. That's called a binomial coefficient. It encodes a formula for counting the paths that will get you whatever number of successes you want. So that N over K, or N choose K, as mathematicians and statisticians read that, that's the number of paths. There's probability of success raised to the number of successes. That's like our 88% to the various exponents. And there's that 1 minus p, that's like our 12% in our notes, raised to the number of failures, which you just get by subtracting the numbers of successes from the total number of trials. We never need to use this formula. Let's put a heart right there. We just don't have to, because we have a completely free and openly available to us on any device calculator that does them very quickly and extremely accurate. And anytime the number of trials gets bigger than just a few, like the 3 shots Lillard took, just think how weird and big the tree would be for 10 free throws, or for 20 or 30. You couldn't even draw the tree at some point. You'd need a blackboard. And even if you're using the formula, the calculations here for the factors with exponents, that's not that bad. But this N choose K, the formula for that's basically a fraction that involves a lot of arithmetic to solve. And if you want to do, like, there's some questions where it wouldn't make sense to try to work through that by hand. I'll put it that way. Especially for larger numbers of trials. Like even here with K number of free throws Damian Lillard makes out of 20 attempts. Well, that'd be too many for me to draw that tree, but I can do these calculations quickly and accurately with my buddy GeoGebra. Let me just take some notes here on the side of what we're going to calculate. So that first bullet says, what's the probability, capital P, that Lillard makes 13 free throws? So that's that his outcome K is exactly 13, equality. What is the probability that he makes at most 15 free throws? Okay, capital P for probability. K at most, that's up to and including. So any number less than or equal to 15 free throws. Relaxing. Just getting the words into symbols here. Third option, what is the probability Lillard makes more than 17 free throws? Hey, I know that in math, K, but I want that number to be greater than, bigger than 17. And the last one says mean and standard deviation of capital K, the number of free throws Lillard makes out of 20 attempts. And you're going to be pleased that GeoGebra will help us with that calculation as well, especially if you can remember how complicated it was to figure out the standard deviation of a random variable back in section 3.5, the formula's kind of complicated. But here actually the formulas are simplified because of the situation, and we have our buddy GeoGebra to help us out. So let's go look at these over in the world of GeoGebra. Now in this world, I'm not going to ever grab my pen to draw a little bell because we've got these chunky looking distributions, and how chunky they are and how skewed they are depends on both the sample size, tells you how many chunks you're going to get. We're bumping it up to 20. And the amount of skewness you see, well, it depends on, what the likelihood of success is. With 88% chance of success, the peak here is around 18. That's the most likely outcome. It falls away in both directions, but it's got a lot more ability to fall away into very, very unlikely events, like making only 12 free throws out of 20 would be ridiculously unlikely, less than a 1% chance. Oh, heck, and then there's our question. What's the probability of making exactly 13 out of 20 free throws for Damien? Do you just see it on the list over on the right? These are the outcomes. Just cruise on down. There you go. About 0.5% chance of making exactly 13 of 20 free throws. Oops. Oops. For 5.3% chance of making exactly 13 out of 20 free throws. Yeah. Pretty relaxing. And you can see, like, I just selected using my mouse. I just tapped the number here on the list. You can do that whenever you've got it set to interval, so that between two values setting, you can just like grab the two values or grab a couple of values with your mouse. Wait, how do I do that? You can scooch the numbers around in here to change which ones you're looking at. Oh, they're backwards. I see what happened wrong. See that? If you get that blue area, you can just find the likelihood between any two values, or you can scooch them both into one value. Or just type, from 13 to 13 down here, and you're exactly at 13 on the list. So it's cool that you get the list and the picture and the symbols down at the bottom of the screen to all agree, so you know you've got the right thing. Oh, come on. Okay, so, and then when you've got the less than or equal option for the second challenge here, probability Lillard makes at most 15 free throws. Well, the good news is when you go to the left-sided option, the bracket pointing to the lower values, it's set to less than or equal to, so it's good to go in GeoGebra. Just make sure it's 15 right here in the input, and the chance there is 0.827. No problem. And they're all lit up both in the picture. Well, you can't see the close to impossible options, but you can see all the possibilities all lit up in blue, all the way up to and including 15. Nice little visual double check that you're looking for the right probability. Pretty cool. It's kind of like, I wouldn't have the confidence to draw these bars like I do to just draw a bell for the normal distribution, because I don't know like how quickly things should break off always. But I do, once you get used to using this tool, you quickly get used to, visually double checking that you got things entered correctly. Like you can look at the picture and look at the list of values on the right to double check you're getting the probability you want. That's useful. Or 8.3% chance of making at most 15 out of 20 free throws. Yeah. It does get a little tricky. Our third option here, probability Lillard makes more than 17 out of 20 free throws. We want to be careful because when we switch over to the right-sided option here, notice it's still, well, it switches around the way it's written, so they put the number less than or equal to our value, our outcome. So we just got to adjust that. Strictly more than 17, kind of put it in my notes. That's like probability that you're at least at 18, right? See what I mean? Like that's kind of the GeoGebra style number first. So I switch the order to go less, but I've got to include the equal to. To get more than 17, I've got to start at 18, then go up, right? Just double checking. And as soon as I plug in the number, 18 down here, visually I can see everything that's colored in is more than 17, right? So just double check visually that things make sense to you and things should generally work out. Yeah, Lynn.
I see for this one, it doesn't apply because you can't make like half of a shot.
Right.
But if it's something where you can, would you want us to put like 17.11111 or something like that?
The good news is that will never, ever happen. This whole setup only works when you're talking about whole numbers, a certain number of random events or random trials, and how many a count of successes. Doesn't even make any sense to go between the numbers. When people want to do that, they use smooth curves like the normal curve for these kinds of calculations. So yeah, great question though. And answer is, you won't have to worry about it, which is a nice answer in this world of complicated calculations. 5631 after a decimal, or 56 3/10% chance of making more than 17 FTs, free throws for short. Okay, mean and standard deviation for the random variable. Well, what's the symbol for a mean in the world of probability distributions? Which Greek letter is it? Mu. It's the U with a tail on the front. Hey, look there at the top, right below distribution, says mu is 17 6/10, and that's great. Mean is mu is 17 6/10 free throws out of 20 attempts made on average. Average, as I type it, average. But and standard deviation symbol is sigma. It's right there. With standard deviation of sigma equals 1.4533. Free throws out of. And visually, the mean and standard deviation work just like they work in data sets. If we draw in the mean with my favorite orange pen from chapter 2 at slightly more than 17.5. Oh, it's not orange, it's blue, but that should be the balance point of that data set. You buy it? Like if all of the bars had equal weight, regardless if they were blue or white, that should balance them out visually. And then the standard deviation of slightly less than 1.5. If I just draw in, well, I don't know, from there. Oops, that's not the symbol I want. Where's my drawing tool? That one. Something like that to get down there, and something like that to get up there. Would you buy that that's on average the distance of all that probability in that graph from its mean? It should visually work for you the way it works in a data set, even though this is a picture of probability rather than data. So once you've got these calculated, they're easy to see on the graph, which is kind of cool. Yay, standard deviation and mean. They also have lovely formulas that we will soon meet on the slides. Yay, GeoGebra, thanks for all the nice calculating. Very, very accurate, very quick, very relaxing. Once you recognize the situation, set number of random trials, set chance of success, question about how many successes out of a certain number. Here's your tool. I'm just going to dump this drawing also into our notes just because it's got all these results. It's nice to have those somewhere to see if we like. Okay, another example here. If the probability of developing a severe lung condition for someone who smokes is 3/10, 30% chance, what is the distribution of the number of cases of severe lung conditions among 4 random people who smoke? And I'm saying find these probabilities using technology with the important idea. We've got a set number of smokers, that's 4. And we've got a set probability for each of those people of 3/10 of developing a severe lung condition. So my grandma would be an example of a so-called success here because she died from emphysema. Wait, there's the problematic nature of that success label. Yes is the better label. Yes, someone's got a severe lung condition, rather than thinking of it as success to develop a, harsh health situation. But all I'm going to do, once I notice that's fixed, to get all those probabilities all at once, I just head over to GeoGebra. I dump 4 in for N and 3/10 in for P, and all the numbers appear before my eyes, which is just nice, relaxing. Once we recognize set number, 4 smokers, set likelihood, 3/10 for an individual smoker to develop a severe lung condition. And there in our, we can see the probabilities for 0 of these 4 people, or 1 of them, or 2 of them, or 3 of them, or all 4 developing a severe lung condition. The good news is the least likely outcome is all 4 people. Maybe the bad news is that the chance of at least 1 person among 4 ending up in a rough health situation is about 76%. So for only no one to develop a lung condition, that would be only a little bit less than a quarter of a chance. So again, if anyone needs any smoking quitting tips from an old successful quitter, let me know. I'll tell you my strategy. And of course, I understand all the challenges of quitting smoking. So no pressure, obviously, because that doesn't help. If you're ever interested or just want some support, come talk to your old stats teacher. Okay, I think on the slides, they also have for us, they're using the formulas to get these calculations done. So if you happen to know how to use this 4 choose 0, 4 choose 1, 4 choose 2, these funny looking binomial coefficient numbers, they're these interesting calculations that tell you how many paths through the tree that would model this you're going to get. Cool. And then the formula gets us the same exact probabilities that we calculated instantly with GeoGebra. They just rounded them off to 3 decimal places instead of 4. Relaxing. So relaxing. Good times. They also made the graph. They used a computer to make their graph just like we did. Ours happened exactly at the same time we calculated the likelihoods. So GeoGebra really does a nice job letting us see the model and also deal with likelihoods. And then it notes here, like any probability distribution, binomial distributions have a mean and a standard deviation. We already know that from our previous example, and we can see the mean here is if you look at a bunch of different groups of 4 smokers, and everyone has that same 3/10 chance of developing a severe lung condition, then on average, you'd expect 1 2/10 people out of 4 for different groups would develop a severe lung condition, and the standard deviation is visualized here, and the value is a little more than 9/10. Kind of tricky numbers to think about until you start to feel comfortable with expected values and variation in probability, but they're there, and they also have straightforward formulas. Oh, if you want to think back to chapter 3, section 5, when we met random variables with outcomes or numbers with corresponding probabilities, we talked about a racehorse, we did a tree diagram, and when we were done, we used these 2 formulas to find the expected value, E of X, or the mean of the random variable mu. Both symbols are popular, along with its standard deviation. Well, those formulas still work, but they're drastically simpler in the case of the binomial distribution because everything's so much more predictable. We know that we're talking about this specific situation with this lovely pattern to the probability calculations. When you throw that pattern into these formulas, things simplify drastically. The mean, oh, they're going to give us an example. The mean is actually intuitively sensible. A 2012 Gallup survey suggests that 26 2/10% of people in the states met at that time the current definition of obesity. Among a random sample of 100 people back then, how many would you expect to meet that definition? Yeah, the closest whole number is 26. So 26.2%, well, percent is out of 100, so you would expect 26.2. And I didn't even do that multiplication. I just know that percent means out of 100, so I was good. But if it was any other sample size, we could have just multiplied the sample size by the probability to get a good idea what you should expect. And we could, so there you go. There's the symbol for the mean value of the binomial distribution. You just take the sample size, multiply it by the probability of a yes or of a so-called success, and you're going to get the mean or the expected value in that situation. Of course, that doesn't mean every random sample of 100 people would have 26 2/10 obesity definition meeting people in it. There's no 2/10 of a person, but there's going to be variation, right? Sometimes more people than that, sometimes fewer people than that. And if you have lots of different samples of 100 people, on average, the number meeting that definition back then should have been 26 2/10. The tenths are fine because we're talking about an average. Bonus note, let's fight fat phobia and support people of all weights and shapes and sizes being healthy and cool. Being big doesn't mean people are unhealthy and is not a moral feeling of any kind. Please push back against that when it comes up in daily life for you, if you can. Like if you hear someone make fun of someone for their weight, do the cool thing that would convince them to not do that. Whatever that cool thing is, depends on how your relationship is with the person who makes a harsh comment. So there's the mean formula, just number of random trials times probability P of so-called success. And the standard deviation, sigma's formula, is just slightly more complicated. It's the square root of a product of 3 numbers, the sample size n, the probability of a so-called success p, and the probability of a so-called failure 1 minus p. Relaxing, just straightforward calculations, though for us, we don't ever need to do these calculations by hand if we don't want to. Even the standard deviation one, it's 100 is the number, 262 after a decimal is p, probability of a yes to the question. If I just dump those into GeoGebra, 100, 262 after a decimal, there's the standard deviation, 4.3972 with 4 digits of accuracy waiting for me, along with the correct expected value or mean, relaxing. So 4.4 if you want to round off to a 10th, and that's exactly how we would round off in GeoGebra. Very, very nice. Yay, technology. Thank you so much, volunteer developers of GeoGebra, for sharing your expertise and this lovely tool with us. And there's that conclusion we would expect back in 2012, 26 2/10 out of 100 random sampled people in the States to meet that obesity definition on average. Throw that phrase in and it makes a little more sense, with a standard deviation of 4.4 people. And once there's a feeling for that being an average, and that the standard deviation is the difference between different samples variations, the numbers start to feel like they make sense. Until then, they're just numbers we're talking about in stats class on the homework. So, take a moment to think about what they mean as you work through your homework, and you'll more deeply develop your statistical literacy. The dream. Oh, and a reminder, both the mean and standard deviation of a binomial distribution are not likely to be whole numbers. It's because they're both averages in different senses. One's the average outcome over lots and lots of trials for that number of trials, and the other is the variation we expect across those, which is an average distance. There's not likely to come back right on the whole numbers in that setting. Unusual observations. Using the notion that observations which are more than 2 standard deviations from their mean are considered unusual, means and standard deviations like we just computed can come in handy to get like a plausible number of how many people you'd expect to meet that obesity definition in a random sample of 100 people. You can see they're just taking, here's the mean value, 26 2/10 out of 100 people on average, meeting the definition, add and subtract to and from that mean, double the standard deviation. That gets you like about 95%, for 2 standard deviations. And that takes you down as low as 17.4 and as high as 35. So if you're a person who deals with people's weight in your work, like a nutritionist or anything like that, and you have goals based on obesity definitions, or just are using this definition in a non-discriminatory health supporting way, anytime you worked with 100 people, you'd be not surprised if between 17 and 35 of them met the obesity definition. It's not a large group, 100, so the standard deviation is going to be pretty big, and wide variation, like 17 up to 35 is pretty wide variation on the scale of 100. Not surprising. And the more you learn about how that works, the more it feels normal. What do we have? Oh, it's 5 minutes past the hour. Want a break before we look at more numbers? Yeah, let's take our last break. We'll be back here at 15 minutes past the hour. Cool. Get some fresh air if you're near a fresh air option. I think the rain is back here in Southwest Portland, so stay dry as possible wherever you are as well. Fresh air and dryness being the ultimate break combo.
So, what does? What is the? Yeah, the number, what's the number? What's the? Yeah. And then ask. What's probably the average of 245 friends and 70 or more friends. Have 70 or more. Neither of our answers are correct. But how are you supposed to know that from the question? Except for usually it's by no. Same thing. Yeah, what I mean. Like, why isn't it? Why doesn't it work? Because like high school, you don't really get it.
49.9. They go by meters and gallons. The time is already, that is how much. There's.
Late, but we did well. We're back. Back we are. Let's talk more about the binomial distribution. This little example here An August 2012 Gallup poll suggests that 13% of people in the States think homeschooling provides an excellent education for children. It definitely can. I've met some adults who I've taught as students here who were homeschooled up until they came to PCC, who were absolutely great and engaged students. I don't know if that means it's true for everyone, because it's a very diverse group of people who do homeschooling. But so they're zooming in our attention here on just this 13%, just that one. That's the excellent option for homeschooling, in a much more complicated data set. Well, there's lots of other options for levels of and we're talking about different kinds of school, independent, private schools, parochial or church-related schools, charter schools, homeschooling, and public schools. Okay, would a random sample of 1,000 Americans where only 100 share this opinion feel unusual? 13% chance of a yes. Would it be unusual for only 100 to share the opinion? Want to see one way to think about it that I think of? And then I think the slides makers think of it a different way. I notice this is a set probability, 13% chance of a yes. This is a set number of chances for a yes, 100 people being asked, 1,000 people being asked the question. So that sets the number of chances for a yes at 1,000. That's it. N is 1,000. 13% is the likelihood of a yes. And to see where 100 falls in the picture, I can just look at GeoGebra and get a sense of how likely it looks quickly. Let's just go peek, knowing those three numbers. Clean up my mess. I said there's 1,000 people here. Notice the bigger and bigger the N gets, the littler the graph gets, because there's always going to be a lot more ways it could go that are very, very unlikely. There's basically no chance that all 980 people would say yes to that question here. And that's true all the way down somewhere into the high 300s. There's no chance that 0 people up to somewhere around 180-ish people, there's just very, very low or no chance of that happening. But I'm at the wrong likelihood here. Then you go to 13%, shifts the thing down, so now it's centered at 130 is the expected average there. And 100, does this number here, that 100, does that look unlikely in this world or likely? We could look at it, one way statisticians might look at it is to think of up to 100, so 100 or fewer. That's one way statisticians might peek at it. The chance of being up to 100 or below, you can see now the marker is set there better than my little arrow for 100. There's less than 1% of groups of 100 would have, less than 1% of groups of 1,000 people would come in with 100 or fewer people saying yes to the question. Feel unusual? Yeah, unusual. Kind of like when we looked at hypothesis testing. If you set a curve and you end up out near the very far edge of the curve, things feel unusual. And also here, I think one of the book's ways to think about it is when you know the mean is 130 and the standard deviation is 10.6. Let me do a little math. Whenever you take the mean, we're looking at a number that's below the mean, right? 130 is expected. So if I subtract 2 times the standard deviation, that number is going to be 130 minus 2 times 10.6. I'm tired. That's 130 minus 21.2. Is that right?
Yeah.
And that's 130 minus 20 is 110. Minus 1 more is 109. Minus 2/10 more, is that 108 and 8/10? Am I right? I mathed that? See that? I did multiplication and subtraction when my head hurts. I read a book about how to do those once. But that's two standard deviations would be two standard deviations below the mean, and 100 is below that. Rare, right? That'd be a rare sample that would come back two standard deviations below your expectation in this world. And it looks like a normal distribution with this very thin, consistent relationship of binomiality here. So yeah, I'd say looking at it either with the little area finder at the bottom or just thinking in terms of standard deviations, this feels rare to me. Let's go see how the slides answers the question as well. Hey, there you go. They went and found the mean, 130. They used the formula instead of, so they just took 1,000 times 1300ths. They found the standard deviation sigma using the formula, still 10 and 6/10. There they went the range of usual observations. They calculated our 108 and 8/10, the lower boundary, and they did the upper boundary, but I didn't care about the upper boundary, but 100 is not in that range, so it feels unusual. Oh, and a bonus method, if you remember back from like sections back now, z-scores, remember them from like the normal distribution world? When you've got a world that is unimodal and symmetric, and you want to see how far from expectation you are, you can think of it in terms of standard deviations. So if you find the z-score here, 100, subtract away the mean of 130, divide through by standard deviation of 10 and 6/10. There's our little z-score formula, number minus mean divide standard deviation. Well, that's noticeably further from 0 than -2. It's -2 and 8300ths. That's almost 3 standard deviations below the mean. Hey, so that's unusual. More than 2 standard deviations from the mean. You can see it multiple ways. I'm going to call the dentist after this afternoon at some point. See what they have to say. Okay, things go dark gray here because there's some kind of optional topics. They're interesting though. Let's look at this one. This is a slide where they're showing us if you set the probability of a yes or so-called success at 10%. I'm going to look at it over in GeoGebra. Probability of a success at 10%. And they're saying, let's look at some different sample sizes. Sample size 10, or sorry, number of trials 10, 30, 100, and 300. And they're asking, what happens as the sample size increases? Well, there's a couple things that are kind of obvious, but a couple are less obvious. So let's look over here. Starting at sample size 10. I'll just ask the questions. Is that symmetric or skewed? Skewed. Cool. Let's go sample size 30. Is that symmetric or skewed?
Skewed just a little.
Skewed just a little. And I think you can, I see it graphically because while the center of this graph, I can even draw a normal graph on top of it that has the same mean and standard deviation. The center of the peak is right there. It just doesn't have room as you get down to 0 as you go off to the left. You have plenty of room to the right to have the whole tail, but off to the left, you just run out of space. So it's skewed to the right where you have space. Okay, let's gaze upon sample size 100. Symmetric or skewed? What if I put this normal curve on top? Symmetric or skewed? Sorry, everybody who's talking is talking just slightly quieter than the hum of the computers and my badly ringing left ear. So, what are you saying? I couldn't hear anybody. Slightly skewed? You might see a slight skew, or you might say symmetric. Let's go one level further. Let's go one level further. 300. I'll leave the normal curve on there for comparison. How about that one? Symmetric or skewed? Symmetric. I mean, the little red line doesn't exactly match the blue jagged things, but that's just because of the way that the numbers kind of line up as terms of whole numbers and smooth numbers. Yeah, this is very symmetric. And you'll notice if we look over at the probabilities of being, you know, like the peak here, the expected amount is 30. That's, you know, 10% of 300. The probability for 30 is pretty small. It's only about 7 6/10%, or between 7 and 8% chance of being right in the middle. And as it drops away toward the lower values, you can almost see like at 12 yeses or so-called successes, and then as you get to 11, right there on that scale, I'm getting into the zeros for probability, and I can see that the tail going that way does kind of meet the horizontal axis. I can no longer see any likelihood there. And let's go backwards down to sample or number of trials 100. This one got a little more of a slightly skewed vote. But even here, notice that outcome 0, like 0 yeses or successes here, the chance is 0. So visually, even though there's like this like blue line that's very, very small poking off to the right, from 24 up, all those are about probability 0. So we don't worry too much about being out there. When you get down to 0, you can think of the tail as not having weight. And here in both directions, it gets down to 0. That's good enough for statisticians. So at 100, a statistician would tell you this curve here is symmetric enough for us to think of it like a normal curve. All of our eyeballs for sample size 30 and sample size 10 said skewed. And you can see when you look back at those sample sizes here, down at outcome 0, well, there's a visual noticeable likelihood of 0 successes out of 30. It's about 4% chance. Or if you dump it down to 10, it's even more likely to be down in that 0 bin up to like 35%. So, but if there's space to get down to a 0, like here the zeros start at 7, 8, 9, 10. If there's space in both directions, statisticians are like, well, that's close enough to symmetric for us. Now, nowadays, this isn't a big deal because whichever sample size you choose, 10, 30, 100, and 300, if I give you a question about probabilities for various numbers of successes out of any of those numbers, 10, 30, 100, or 300, you can just use a calculator to quickly give me the probability result back. It wasn't always like that, though. So in olden times, for larger and larger numbers of trials, statisticians would often switch from the binomial distribution over to the normal distribution, the smooth curve. Because when you get up to like 300 here and it looks really smooth, there were like calculation issues in the days before computers that it was a lot of work to answer probability questions like the ones we can ask about, you know, what's the likelihood of more than 40 successes here? Would be hard to do in the olden days because you've got to talk about tons and tons of calculations for all those little bars that have more than 0 likelihood. And the calculations just get harder and harder the bigger the sample size gets, or the number of trials gets. In any case, what I'm trying to say is in olden times, they cared that you could expect 10 or more successes and failures, because in that setting, that's like 10% of 100, right? That's enough space to get tails in both directions. So don't worry about that little abstract example there. But, oh no, these are the numbers we saw before. 30 times 10% is about 3. That's way less than 10. So you're not going to expect to see a normal shape distribution or a symmetric one. But if you have 100 trials with 10% chance of success, you're going to end up with 10, at least 10 in both directions, 10 successes and 90 expected failures. That works for this normal, for using a normal distribution if you'd prefer. Big deal in olden times. Not as much of a big deal nowadays. Yeah, it all works together. Okay. Let's just skip this one because it's kind of boring, this little practice thing. I would never ask you a question like that. I don't think you need to worry about it. But here's a nice question that we can answer. And well, sorry, this is a prequel to a question that I think is our quiz question. So, and we're back to a bright colored slide. We can use GeoGebra to answer this kind of question. Well, the question's on the next slide. Here's some information. A recent study, so that's probably about 2012-ish, found that Facebook users get more than they give. Now, I know that not everyone's a Facebook user, so just think of whatever social media you do use, if you use some, or that your friends use. And I'm just going to say social media instead of Facebook. 40% of social media users in their samples made a friend request or requested a connection. Those 63% received at least one request. Users in the sample pressed the like button next to their friend's content an average of 14 times, but had their own content liked an average of 20 times. Science. Users sent 9 direct messages or private messages or personal messages, whatever they're called, but received about 12 on average. 12% of users tagged a friend in a photo, which was a Facebook. I think Facebook still does that nowadays, but it's not as popular as it once was. But 35% were themselves tagged in a photo. Okay, why is that? What explains the pattern? Does anybody with an average, thinking about averages, feelings, point them somewhere? Why would you, on average, get more from social media than you give? Ben?
Well, one, it could be your sampling bias. Like maybe I don't know, people that were more popular, or they're more, I guess, I don't know, like popular in realm of social media, like more of those people were sampled than people who weren't, or maybe it was just an unusual occurrence.
Let's trust their sample, because like any social media study you want to do, if you can get the cooperation of the social media company, they have all the data. So you can get a random sample, perfectly random sample, any size you like, if you can convince, say, Facebook or Meta, what they're called now, to share their data with you, to learn more about Instagram, Facebook, and all the rest of their social media empire. So let's trust that. But your second observation is good. Say it again.
Unusual occurrence.
Unusual occurrences. I've got a friend on Facebook of someone who's just turned 59. So he's a perfect Facebook user, exactly the right age, a Gen Xer. And he's a good Facebook friend to have if you like music and he's someone you know, because when he's bored in the evening, he will share like some nights like 20, 30, 40 like photos of bands he likes or songs he likes, and just make little comments that are in his, witty way. And it's fun to get all of that stuff, right? Like a lot of stuff kind of comes to my feed at once from my friend Wayne, and I'm happy to get it. Now, that's way more than I put on Facebook, right? I'm like a 1 or 2 memes a day sharer, or I share like a video once a week, stuff like that, like habits. But it turns out that most social media users are more like me. Most people don't post a ton, though they'll know at least one person who does post a lot, right? And in a world where some people even make money on social media, whether it's TikTok, Instagram, etc., there's lots of ways to share your work or generate revenue in the social media world. They're called power users. They put more stuff, they put more content into the system than people typically do. So Wayne, relative to me, is a power user, though he probably is not a power user relative to like a, good one. Isn't it?
Somebody's better.
Yeah, so that's the idea. That the rare event is that people do post a ton and that drives up the averages. Okay, the study also found about 25% of Facebook users are considered power users. So this is back in 2012. I'm sure these numbers would be different today in different social media settings. The same study found the average Facebook user at the time of the study had 245 friends. What's the probability that the average Facebook user back then with 245 friends had 70 or more friends who would be considered power users? Ignore the assumptions we need to make. We'll just look at the note below. We're given n, the number of possibilities here in this random world is 245. That's set number. And the probability P is set. Any individual person here has a 25% chance of being a so-called power user. And we're asked for the probability that we come in with 70 or more power users among the 245 people, P of K greater than or equal to 70 for short. Oh, they do note one assumption. To proceed, we should be able to assume that none of the people's power user status impacts any others. I don't know if that, I don't have enough information about social media to know if that assumption makes sense. Socially, to me, it feels maybe like it's not independent, really. Like if I like Wayne's posts and he posts a lot, what if I'm starting to like all of Wayne's posts? That's, since I have a power user friend, I'm doing more interaction, right? So I think there's, but ideally it would just be random people among all the friends, and it'd be completely random who's a power user or not. In any case, we can make this a quiz question for today because we have all the tools to calculate this likelihood quickly and accurately. I'm going to go to coursework, quizzes. I'm cruising on down to the binomial distribution quiz. Details boring, start quiz. Oh, you keep seeing the face of pain I keep making. My face is killing me. Okay, same question. A study found about 25% of Facebook users are considered power users. That's my P, 25%. The same study found that most people, or on average, people had 245 Facebook friends back then. That's a set probability of a yes to that question. You a power user. This is a set number of people. And we want to know the probability that a Facebook user has greater than or equal to 70 power using house. Did you do that using our little buddy GeoGebra? Do that using our little buddy GeoGebra. If you're in the Zoom world, when you're done, drop your results in the chat. If you're in the Sylvanian world, when you're done, share, wait a few beats to give other people a chance to finish. And then, double check your result with a neighbor or with me. But we need at least a couple of you to agree, and then I'll double check it. I'll triple check it for everyone. Okay, we have a nominee in the chat, so if you're in the room in Sylvania, check if you get the same value as mine in the chat. And if you can't read it where you're sitting, just ask me and I'll say it for you. Depends on your vision, if you can read our chats or not. And always remind me if something's too small to see on the screen. And if anyone else out in the Zoom world is double checking Maya's result, you can just give it a thumbs up if you agree, or if you get a different result, you can, share that different result. And then those of us in the room or Zoom, sorry, Sylvania room or the Zoom room, you just all want to make sure that we're all in agreement. So, thumbs ups work if you agree with my little reaction there. Or you have a different value, let us know.
I got the same thing.
Hey, cool. We got a couple thumbs up in the classroom, so I'll put that thumb up here. We're getting a thumb up from outside. Yeah, we're getting multiple thumbs up in the room. Thumbs are beginning to go up. All right, cool. Good work. I'm with y'all. Let me just show you me walking through this calculation as well. I go over to GeoGebra. Where's my, there it is. I go to GeoGebra. I've got my notes right here. I set my probability at 25/100ths. What is going on? Oh, I see. I set the number at 245 people. Ancient people of 2012 on Facebook, back when we were 13 years younger. So when Facebook was mostly in their 30s and 40s instead of their 40s and 50s and older. But there's our picture, and I want to find greater than or equal to 70. I can see from the graph it's not going to be super likely, but there's definitely going to be a number. Dump in my 70 for comparison, and I've got a 0.1128, just like mine. Let's go for a heart for the chat response. Now we're in full agreement with the class. And then when you want to get your point for this one, note there's a little style note in the quiz. I know not everybody reads the style note, but let me make sure you see it. Sorry, I got a mess here now. Notice right here, enter your result accurate to 4 decimal places, starting with the 0 and the decimal. So it should look exactly like my typed it up in the chat, 0.1128. My D2L's grading system for write something in a field is it just looks and sees if you have exactly the same characters. It won't even know that's a number. It just knows it's a 0 and a decimal or a period, a 1, a 2, and an 8. So enter it just like I have it written here, then hit respond, and you should get full credit for your good work. Yeah? So make sure the style looks just like mine and like Mai's, and you'll get it, you get your point. Yeah? That's the first time we had to dump a number in this thing the whole quarter. Kind of fun, kind of a fun change of pace. But yeah, so type like this and then submit that quiz, get your point, and you are one more quiz closer to all the quizzes being done. We can actually kind of see the end of the path through the quarter as we get closer and closer. All right, cool. Great work. Now let's go back. I think we have now, my notes, it says, let's use technology to calculate this one. We just did that. Let's see how this was done in the days BC. That's before computers. Back in the days before computers, where you didn't just have access to a binomial distribution calculator that you could use any number of trials or sample size you like. You could enter the amounts and get any probability you need. Before those days, people used the normal approximation to the binomial distribution. In that case, they would switch from the chunky binomial curve we just used in our work over to a smooth normal curve by using the formulas for the binomial distributions, mean and standard deviation. You can see they have a black binomial chunky graph with a blue normal curve. For us, it's this normal curve here. It has the mean 61 and 2500ths and sigma standard deviation 6 and 7777 10,000ths. Then they could just use the old-fashioned how to find the area under a smooth curve, because it was the days before computers. They'd switch to a z-score that says 70 is 1.29 standard deviations above 61 and 2500ths in this world, so a z-score calculation. And then they'd look in the back of their stats book or their book of statistical tables and see that the probability of it being that way is about, or at least 70 or more in this setting, is a little less than 10%. And so they're off. They're off by, a noticeable, like about 2%-ish, up 1.5%, something like that. So it's another place where you might see some of the results in the back of the textbook when there's a large number of trials or a large sample size. I would encourage you to use GeoGebra for quick, accurate, modern calculations, though you may see some funky notes in the back of the book about z-scores and probabilities that are off by 1% or 2 from your results. Shouldn't surprise you. It's just a hangover, again, of an anachronistic method that sticks around because, of course, not every stats professor is underage. Well, so let's just say we're not all off Facebook yet. How's that to describe our age as a group? That work? All right, and that's the end of this slideshow, and it's perfect timing because we ran out of class time, although it's also a little sad because we didn't at all get to talk about today's scheduled topic, although that's not the worst thing on planet Earth. What we'll do next class is, knowing that we need to talk about sampling distributions to kick it off next class, we'll just start right there. So we'll start right there on Wednesday. Like I'll skip the any homework questions next class, even though we had a lot of great ones today. We'll try to get the business done first, and then if we have some time remaining at the end or on the breaks, I can think about homework questions with people who bring them in. Let me know on the break, and then we can figure out if we can answer them on the break or have a class-wide discussion at the end of class for homework. And that way we can get as close as possible to talking about these big topics next class. All right. Oh, and last thing, regardless of my face pain today, I've sworn upon my heart to do as much exam grading as I can today and catching up on scoring homework. Wish me strength and luck. I'll take only the shortest possible break to call a healthcare provider if this face keeps bothering me. All right. But we'll try to get caught up on stuff today. So yeah, as best we can. As best we can. Some of you will find your exams are graded today. Some will find they get graded Tuesday or Wednesday. Wednesday is the last day. I'm done Wednesday. I promise you. I'm done being distracted or sickly or whatever. I just gotta focus. All right, farewell.